Okay, on problem 342, we've got a free body diagram here, but what we're going to do is we're going to split these out. Now this force would end up being 15 kips sine of 75 degrees, and then we also have a 15 kips here, which ends up being going to the right, and that is 15 kips cosine of 75 degrees. Then we have another force here that's doing this, and that is 25 kips cosine of arctangent of 12 over 5 is 67.38 degrees. And up here then we've got another force that's vertical, and it's 25 kips sine of 67.38 degrees. So that's the free body diagram we have to deal with. So then we'll do reaction. Now again, as I showed you in class the other day, we have to do a reaction at X, and that's going to be 15 kips cosine of 75 degrees. And that's a positive value, it's going to the right. Then we've got minus 25 kips cosine of 67.38 degrees, and that's all we're given. So we'll do the math on that, and we find out that we've got 5.73 kips to the left. It came out a negative value, so it's going to the left. Excuse me. Well, then we'll do a reaction relative to the y-axis. We've got negative 10 kips minus 15 kips sine of 75 minus 25 kips sine of 67.38 degrees. Do the math on that, and you'll find out that that's a negative 47.57 kips. Since it's negative, it's going down. Well, then to find the resultant's final force, if you will, magnitude, reaction, or the resultant force is the square root of the 5.73 squared plus the 47.57 squared. Do the math on that, you should end up with 47.91 kips. Then we need to find the angle for that bad boy. So theta equals the arctangent, or inverse tangent, of y, which was 47.57, divided by x, which is 5.73, Do the math on that, and you end up with 83.1 degrees. So the resultant, if you will, equals 47.91 kips at, let's see, now that's going down and to the left, so that's about the third quadrant in it, at 83.1 degrees. Well, that's the biggest part of the story, but then we have to find out what X bar is. In other words, how far from O do we go over to put that in? And to do that, we're going to do a summation of the moments relative to O. So we got the 10 kips. That makes it a negative. It's going clockwise. Times 8 feet. Minus 15 kips. It's going clockwise as well, right? If it spins. 15 kips sine of 75 times 8 and 6, 14, right? Minus 25 kips sine of 67.38 degrees times 5 and 6 is 11 and 8 is 19. Do the math on that. Oh, by the way, the 15 kips cosine of 75 and the 25 kips cosine of 67.38 go through that point O. They don't make it spin, therefore we don't use them in the moment equation. So we end up with 721.3 kips, and that is a negative value. Kips feet, sorry, excuse me. Kips feet. It's a negative value, so it's going clockwise. Okay, so to find X bar, we just go in there and take the moment, the 721.3, divided by, in this case we take the reaction force at Y, and that's going to be 47.57, and this was kips feet, and this was just kips, sorry. Start to put feet. Kips. Kips cancel out and we're left with feet. 721.3 divided by 47.57 is 15.16 feet from point O. Okay, now why did we use 47.5? Anytime you're looking for an X bar, you would use the Y value. Anytime you look for Y bar, you would use an X value. So what we're looking at here is, excuse me, we want to use we know this thing is off at an angle of 83 degrees, but to find out how far it is from this O point relative to the x-axis, we have to use the y component to be able to tell what that distance is. If you try to use the x is actually 0, isn't it? Because it's acting on that beam right down through the axis. So that's what's going on there. And that's the final answer then. It's 15.6 feet from O. Relative to the x-axis. Okay, so that's problem 342. Well, let's see. Let's see if we can't do 344 now. I'm sure we can. First thing, we will draw a free body diagram of this one away from that picture. It's just going to be a little easier, I think, to visualize. So bear with me for a minute here. Okay, so we're looking at a free body diagram that basically, and what's a free body diagram do? It actually just simplifies the picture, doesn't it? So we're looking at a free body diagram that does something like this. We want to put the beam, or this apparatus, whatever you want to call it. So I would normally have an AX probably going here, an AY doing this. Let's see. Now I know I've got a 50 Newton force coming down here. That's a given. Okay, and let's see. Over here we've got an evenly distributed load, so we can put that right square in the middle, and it's 2 meters and it's 40 newtons per meter. 40 times 2 would be 80, wouldn't it? So we're going to put a force right square in the middle, and it's 80 newtons. And again, that was 40 newtons per meter times 2 meters. Meters cancel out, you're left with newtons. The distances on that from here to here is 1 meter, and then the other one is, if you will, this one from here to here is 2 meters. Well, then we've got this unevenly distributed load that's going like right along here. Okay, so now this force, we've always talked about the fact that, you know, this force would be somewhere right here, but note the arrows are going to the right, so that's not going to be the case in this example. What we're going to have there is something that looks like this. We're going to have a force that comes out like this, maybe I can get this pen to cooperate. It is early in the morning, so maybe that's probably what's going on. Well, it's 100 newtons per meter, and it's 4 meters. So that would be 400, but then you have to divide it by 2 because it's a triangle. So that would be 200 newtons. And again, that's 100 newtons per meter times 4 meters divided by 2. Okay, well then we need to have the distance on that. Now again, this triangle is doing something different than what we're used to. That's why it was assigned. So let's see, if we're looking at that, we have to see how far that's up off of this axis, because the force basically is doing this, isn't it? Where it's, yeah, it's gravity, it's not center of gravity, but it's center, and all that force is acting right here, going to the right. So we've just basically rotated that triangle 90 degrees. Okay, so if that's the case, then it's the base divided by 3 to get this number. Base divided by 3 ends up with 1.33 meters from here to here. Then that's basically all we need. Now they do supply a 5 meter total height, but it's really not going to come into play in this example, so we don't have to worry about that. So let's see, we've got our free body diagram. This is one force here, we've got a force here, and a force right here. So we need to do just what we've been doing. We do a reaction we got to do a reaction force in the X. Up too far, sorry. Gotta make sure we can see all the forces. I guess I should have probably left it where it was. There we go. Okay, so we want to list all the forces in the X. So the reaction with respect to X is going to be what? 200 newtons going to the right. That's kind of we like, isn't it? That's the only thing acting, minus the AX. And by the way, AX is wrong here, isn't it? If this is the only force pushing to the right, then this one would actually have to go back to the left, wouldn't it? And I would denote that I had put that in wrong by making a big arrow here and making that arrow go away. So now I know that that would actually go to the left to react against this action. But that's another day. Okay, then I do the reaction force with respect to the Y, and I've got minus 50. Right, the 50 newtons is going down out on the end, and minus 80 newtons for that evenly distributed load. That's all I've got. So that's 130 newtons going down. Then the reaction magnitude for the whole system is going to be the 200 newtons squared plus 130 newtons squared. And we do the math on that, and we end up with 238.54, if you will, newtons. That's all we can do for that. So we find theta, the angle, and that's going to be the arctangent of 130 over 200. And you find out when you do the math on that that you end up with 33.02 degrees. So the reaction, or the resultant, is 238.54 newtons at, and that's going to be, and it's going to the right and down, so it's going this way in the fourth quadrant at 33.02 degrees. Okay, so that's a big part of it. Well, then we have to find out where it's located. So to do that, well, we can fit the moment in there at least. Well, we didn't just create a new sheet. We can go back and find it. Okay, so we'll do the moment with respect to A. So we've got the 50 Newton force here that's going to make this thing go counterclockwise, which is positive. So we do 50 newtons times, it's 2 meters away from AY, isn't it? Then we've got the 80 Newton force, which is also going to make it go positive, clockwise, or counterclockwise if you will. 80 newtons. And it's 1 meter away from A, right here. And then we've got the 200 newtons. Now that's making that thing go clockwise, which is negative. 200 newtons. And that's 1.33 meters away from A. Do the math on that, and you should end up with a negative 86 Newton meters. Since it is, it's positive 86 Newton meters, and it is counterclockwise. Well, then the last thing is the X bar. With respect to A, if you will. Okay, and that's going to be, let me scroll this up a little bit. Now all we need is the moment equation and the Y bar. I think is, yeah, or not the Y bar, but the Y reaction force, I should say. Remember, if you're doing relative to X, you do the Y number. Okay, so we've got 86 Newton meters divided by 130 newtons, and you should end up with 0.66 meters from A. Okay, and that's the answer to that. So that's how you solve those two problems. Hopefully that helps, and you'll be ready for the quiz come Friday.